In 1924, Louis de Broglie suggested that if light has electron, it possesses both material particle and as wave nature, right? According to Louis de Broglie, like photons, the material particles such as proton, electron, atoms, molecules, a piece of chalk, a piece of stone and iron ball possess both material particle as well as wave nature, right? Okay, now let me see the differences between particle and wave nature. What are the differences between particle and wave, right? First let me see the particle. In chemistry, particle means a minute portion of matter. Minute means very small portion of matter. Whereas wave is characterized by its frequency. Okay, first you should know this one. Particle means it is the minute portion of matter, whereas wave is characterized by its frequency, right? Okay. So first one, a particle occupies a well-defined position in space. Well-defined means clearly defined position in space. That is, a particle is localized in space. What is the meaning for localized? Localized means it assigned to a particular area or particular location. That is called localized. Okay. For example, a grain of sand, a cricket ball, powder, clay, many things we can say as examples. Okay. So, a particle occupies a well-defined position in space. That is, a particle is localized in space, right? What about wave? A wave is spread out in space. Already I told you, wave is characterized by its frequency, isn't it? So, a wave is spread out in space. Example, on throwing a stone, okay, on throwing a stone in the pond of water. On throwing a stone in a pond of water, you might have seen the waves start moving in the form of concentric circles, isn't it? This is due to the waves radiate here, okay, due to the radiation of waves. A wave is spread out in space. On throwing a stone in a pond of water, the waves start moving out in the form of concentric circles. Why? Because here the waves radiate in these concentric circles, right? Similarly, the sound of the speaker reaches everybody in the audience. How? Because sound waves are transmitted through the air, isn't it? So, the sound of the speaker reaches everybody in the audience. Thus, a wave is delocalized in space. Delocalized means what? Removed from the particular location. Got it? Right? Shall we move to the second point? Okay. Second point is, when a particular space is occupied by one particle, the same space cannot be occupied by any other particle. It means the particles do not interfere. Interfere means do not take part. Okay. What is the answer? Yes. When a particular space is occupied by one particle, the same space cannot be occupied simultaneously by another particle. Hence, particles do not interfere. Got it? Second one, two or more waves can coexist in the same region of space and hence interfere. Interfere means take part. Okay. Two or more waves can coexist. Coexist means exist at the same time in the same region of space and hence interfere. Interfere means take part, right? Third one, when a number of particles are present in the given region of space, the total value is equal to their sum. Okay, when a number of particles are present in the given region of space, the total value is equal to the sum. It is neither less nor more. Whereas for waves, when a number of waves are present in the given region of space, due to interference means combination of two or more waves. Okay, the resultant wave can be larger or smaller. The resultant waves can be larger or smaller than the individual waves. Okay, so the interference may be constructive or destructive. Okay, so constructive means here the photon waves takes place completely in phase. It takes place in the phase. At the same time, if you take the destructive, interference occurs completely out of phase. Okay, what is meant by constructive? Here the interference occurs only in phase. Okay, whereas destructive interference occurs completely out of phase. This is the difference between particle and wave. So mainly the particle means it mentions a minute portion of matter, whereas wave is characterized by its frequency. Okay, so what is the first point? Particle occupies a clearly defined space, whereas wave is spread out in space, isn't it? Wave is spread out in space. It is characterized by its frequency. Second point, particles do not interfere, whereas waves can interfere. Interfere means take part. Okay. The third one, number of particles are present in the given region of space is equal to their sum. Whereas for waves, number of waves are present in the given region of space. Due to interference, it means combination of two or more waves. The resultant wave can be larger or smaller, or otherwise we can say it is a constructive or destructive in nature, right? So this is a 5-mark question. You have to read this question, children. Okay, you have to go through the difference. What is the difference between particles and wave? And you have to give some examples also for each and every point, right? Next, we can move to experiments to prove particle and wave property of electrons. Okay, first let me discuss about verification of wave character. One is about Davison and Germer experiment. Davison and Germer, in the year 1927, they carried out an experiment. Okay, they carried out an experiment, and it was popularly known as Davison and Germer experiment. So in 1927, Davison and Germer, they observed a beam of electrons. Okay, beam of electrons is nothing but the flow of particles. So they observed a beam of electrons is obtained from the heated tungsten filament, is accelerated, okay, by using high voltage power supply, right? This is the experimental setup of Davison and Germer experiment, right? So when this beam of electrons is allowed to fall on the single crystal of nickel, the electrons are scattered from the crystal in different directions. Okay, the electrons are scattered from the crystal in different directions, right? So this is experimental setup. See, this is the tungsten filament. It is connected with high voltage power supply. Okay, so this is the nickel crystal. This is nickel crystal. This is an electron detector. This electron detector is mounted on an arc. This is the arc. Okay, this electron detector is mounted on an arc so that it could be rotated to observe the electrons in different angles. For that temperature, right? Because of this, the diffraction pattern of dark and bright bands are formed. This shows that what is the experiment we are seeing? It proves the particle and wave, isn't it? So Davison and Germer experiment proves the wave nature of electron, right? So the diffraction pattern of dark and bright bands are formed on the screen. So this experiment clearly shows the wave nature of electron. Okay. So Davison and Germer experiment proves the wave nature of electron. Davison and Germer experiment is important because it proves the de Broglie hypothesis. What is de Broglie hypothesis? De Broglie hypothesis is used to define the wave nature of electron, right? Once again I will tell you, Davison and Germer in 1927 they carried out an experiment, okay, and they obtained a beam of electrons. They observed a beam of electrons is obtained by heating the tungsten filament, which is accelerated to a very high voltage power supply. Okay, begin to move very fast. Accelerated means begin to move very quickly, right? So here in this setup, tungsten filament is placed here. Why particularly tungsten filament is used in Davison and Germer experiment? Tungsten is a metal. Okay, it is used for making filaments in bulbs. It mentions the tungsten, isn't it? Tungsten has high melting point, lowest vapor pressure, and greatest tensile strength. Tensile strength means resistance of the material. Because of these properties, tungsten is used in the filaments for bulbs. Okay, it is used as a filament for bulbs. That is why tungsten filament is used in Davison and Germer experiment. Right. Why particularly nickel crystal is used in Davison and Germer experiment? Nickel crystal is used in Davison and Germer experiment because nickel is a hard silver white metal. Okay, it is a very hard silver white metal and it forms cubic crystals. Okay, it has a malleable nature, ductile nature. Also, it reduces the corrosion. Okay, it has superior strength and also corrosion resistance. Means it reduces the corrosion. Also, nickel can withstand a very high heat. That is why nickel crystal is used in Davison and Germer experiment, right? So in 1927, Davison and Germer they observed a beam of electrons is obtained from a tungsten filament. Okay, it is accelerated by high voltage power supply, right? When this beam of electrons is allowed to fall on a single white crystal, the electrons are scattered from the crystals in different directions. Okay, due to this, the diffraction pattern of dark and bright bands are formed. Hence, this experiment proves the wave nature of electron. Okay, so Davison and Germer experiment proves the de Broglie hypothesis because de Broglie hypothesis is used to define the wave nature of electron, right? Second one is Thompson experiment that you will get the information through pickwards. Next we can move to verification of the particle character. First we discussed about the wave character of electron, isn't it? Now we are going to see the verification of the particle character. So first one, some experiments are proved. Okay, some experiments are proved based on the particle character of electron, particle nature of electron. What is that experiment? First one, when an electron strikes a zinc sulfide screen, a spot of light known as scintillation is produced. This spread anywhere. Okay, so scintillation is localized on the zinc sulfide screen. Therefore, striking electron is not spread out on the screen. Next, we are saying it is localized in nature. It is localized in nature. The localized character is possessed by the particle nature. Okay, from this we can understand that localized character is possessed by particle nature. So when an electron strikes a zinc sulfide screen, a spot of light known as scintillation is produced. A scintillation is localized on the zinc sulfide screen. Localized means assigned to a particular area, but it does not spread. Therefore, striking electron is not spread out of the screen. Hence, the localized character is possessed by particle nature. Okay, so this is one of the experiments to prove the particle nature of electrons. Second one, J.J. Thomson's experiment for determination of the ratio of charge to mass. Along with that, Millikan oil drop experiment for determination of charge on electron. These two experiments shows the electron has particle character. You will learn about the Millikan's oil drop method and J.J. Thomson's experiment when you come to higher standard in detail. Okay, so these two experiments also proves the electron has particle character. Next one is about black body radiation. Black body radiation and photoelectric effect proves the particle nature of radiation. This black body radiation means it is an opaque object which emits the thermal radiation. Okay, a perfect black body is one in which it absorbs all the incoming light, but it does not spread anywhere. Okay, and photoelectric effect. Albert Einstein found this photoelectric effect. Okay, so this photoelectric effect means what emission of electrons. Okay, it means photoelectric effect. It mentions the emission of electrons. Okay, so photons means it is nothing but a small amount of electromagnetic radiation, and photons are always in motion. Got it, children? So, what is the first experiment? Two experiments. One is verification of wave character. Another one is verification of particle nature. In wave character, one is about Davison and Germer experiment. Second one, G.P. Thompson experiment. Next, verification of particle character. We saw the zinc sulfide screen experiment. Zinc sulfide screen, it has a unique quality. Okay, that is why this zinc sulfide screen is used in this experiment. It has some unique quality. Okay, so next one, J.J. Thomson experiment and Millikan oil drop experiment also proves the particle nature of electron. Followed by photoelectric effect and black body radiation experiments also prove the particle nature of electron. Okay, so electron it possesses both material particle as well as wave nature of electrons. Okay, right.
G.P. Thompson experiment. G.P. Thompson, son of J.J. Thomson in 1928, performed experiments with thin foil of gold in place of nickel crystal. Foil means it is a thin sheet made by hammering or by rolling. Foils are mostly made with aluminium, copper, tin, gold, etc. So in Thomson experiment, we use thin foil of gold, whereas in Davison and Germer experiment, nickel crystal was used, right? G.P. Thompson observed that if the beam of electrons after passing through the thin foil of gold is received on the photographic plate, which is placed perpendicular to the direction of the beam. This is the experimental setup of G.P. Thompson experiment. In the left hand side, can you see? It's a radioactive source, that is lead block containing an alpha particle emitting beam of particles. See the fluorescent screen, which is circular in shape. At the center, metal foil is placed. The beam of electrons, after passing through the thin foil of gold, you can see the deflected alpha particles. But most particles are undeflected. From this experiment, G.P. Thomson confirmed the wave nature of electrons.
Good morning, children. This class we will discuss about the dual nature of electron. Dual means what? Two. In 1924, the French physicist Louis de Broglie suggested that if light has electron, it possesses both material particle and also wave nature. According to Louis de Broglie, like photons, all the material particles such as proton, electron, atom, molecule, a piece of chalk, a piece of stone, and iron ball possess material particle. It behaves as a particle as well as wave nature. Right? Okay. So now we will discuss about what is the difference between particle and wave nature. Okay. What is the difference between particle as well as wave? First, we will move to the particle. What is meant by particle? In chemistry, a particle is a minute portion of matter. Okay, minute means very small portion of matter, whereas wave is characterized by its frequency. Okay, so particle means it mentions a minute portion of matter, whereas wave is recognized by its frequency. Okay, next one, particle. What is the difference? A particle occupies a well-defined position in space. Well-defined means, okay, particles do not interfere. Interfere means particles do not take part. Okay, once again I repeat. When a particular space is occupied by one particle, the same space cannot be occupied simultaneously. Okay, simultaneously means at the same time by any other particle. That is, particles do not interfere. Whereas in wave, two or more waves can coexist in the same region of space. Coexist means exist at the same time. Okay, so two or more waves can coexist in the same region of space and hence interfere. Interfere means what? To take part, right? Third point. When a number of particles are present in a given region of space, their total value is equal to their sum. That is, when a number of particles are present in a given region of space, the total value is equal to their sum. That is, it is neither less nor more. Whereas in wave, when a number of waves are present in a given region of space, due to interference, interference means spreading of waves or combination of two or more waves. Okay, the resultant wave can be larger or smaller than the individual waves. Otherwise, we can say interference may be constructive or destructive. Okay, constructive or destructive. Constructive, generally constructive interference occurs when photon waves, okay, when photon waves interact in phase, whereas destructive interference occurs when photon waves completely out of phase. That is the difference between constructive interference and destructive interference. Whereas interference means spreading of waves, okay, or combination of two or more waves. So these are the differences between particle and wave. It is a 5-mark question. Okay, so you should learn the differences between what is the difference between wave as well as particle and what is the concept behind the wave and the particles, and you should give a few more examples for each and every point, right? Good. Now we can move to de Broglie relation. Louis de Broglie, French physicist, who is well known for his research work on quantum theory, predicted the wave nature of electrons, right? So, de Broglie relation is mainly used to define the wave nature of electrons, right? What is de Broglie equation? De Broglie equation is one of the equations that is commonly used to define the wave nature of electrons, right? Louis de Broglie, according to him, any moving particle, whether it is macroscopic particle or microscopic particle, it will have the matter nature. It will have the properties of waves. Okay, hence it was called the matter waves. According to Louis de Broglie, any particle, any moving particle, if it is a microscopic particle or macroscopic particle, okay, will be associated with waves. Hence it was called the matter waves. What is the difference between microscopic particle and macroscopic particle? Already I told you particle means it is nothing but a minute portion of matter, right? So microscopic particle means it is a very smallest particle, whereas macroscopic particle means it is a larger particle. That's the difference between microscopic and macroscopic particle, right? Louis de Broglie, he derived an equation based on the relationship between velocity and momentum of the based on that. Right. So in case of photon, if it is assumed to have the wave character or wave nature, then according to Planck's quantum theory, the energy is given by E is equal to hv. Okay, according to Planck's quantum theory. Here E mentions energy, h is the Planck's constant, and whereas B is the frequency, right? So in case of photon, if it is assumed to have wave character, then its energy is given by E is equal to hv. So this is the first equation according to Planck's quantum theory. Second one, in case of photon, if it is photon means what? It is the smallest amount of electromagnetic radiation, and the photon is always in motion, that is movement, right? So in case of photon, if it is assumed to have the particle character means it mentions the frequency, it is characterized by its frequency, isn't it? So particle character, then its energy is given by E is equal to mc square according to Albert Einstein equation. It's a very famous equation, isn't it? Right. So in case of photon, if it is assumed to have the particle character, then according to Einstein's equation, the energy is given by E is equal to mc square. This is the second equation, right? Now combine the first equation and second equation. This is the first equation, this is second equation. We have to combine this equation. So what you will get? You will get hv is equal to mc square. E is the common. So hv is equal to mc square. The h mentions the Planck's constant. V is the frequency. Here m means mass of photon. Where c is the velocity of light. Okay. So combining equation 1 and 2, you will be getting hv is equal to mc square. Right? Now V is equal to, we have to substitute V. V is equal to hc by lambda. Lambda mentions the de Broglie wavelength. Okay. Whereas V is equal to c by lambda. Now we have to substitute this V. Right? So h for V we have to use c by lambda is equal to mc square. Right? Next step, you take the lambda on the left hand side. Lambda is equal to, then what you will get? If you take this lambda, then you will get hc divided by mc square. Right? Now what you have to do? You cancel one c. Yes, c square is given. C is given. So cancel one c. Then you will get lambda is equal to h by mc. Here we cancel one c, right? Okay, so this is the equation. Otherwise, we can write lambda is equal to h by mv. Instead of c velocity, we can put mv, right? Lambda is equal to h by mv, whereas mv is equal to p. P mentions the momentum. Okay, P mentions momentum. So how can you write now? Lambda is equal to h by mv is nothing but p, isn't it? So lambda is equal to h by, for this mv you put p. So this is the de Broglie equation. Highlight the final equation. These three equations are right. Okay. Okay. So de Broglie equation mentions the wave nature of electron. Okay. From this we can understand the wave nature of electron. De Broglie equation predicts the wave nature of electrons. Got it? Right. Next we can move to spin multiplicity. Okay, spin multiplicity. It means in quantum chemistry or otherwise in spectroscopy, the multiplicity of an energy level. Okay, the multiplicity of an energy level is given by 2s plus 1. This is very important. The multiplicity of an energy level is given by 2s plus 1, where s is the total spin, angular momentum. Here, states with multiplicity 1, 2, 3, 4, 5, 6 are called. For each and every digit we call it as one name, right? For 1 we say the singlets, for 2 doublets, for 3 triplets, and for 4 quartets, like that, so on it will come. Okay, right. So spin multiplicity means in quantum chemistry, the multiplicity of an energy level is defined as 2s plus 1. Then you have to mention what is s. S mentions the total spin, angular momentum, and some states with multiplicity 1, 2, 3, so on are called singlets, doublets, triplets, quartets, etc. Right? So this is the spin multiplicity. Right? Let me move to the activity now. For first activity, you need an incense stick and a matchbox. Okay. First, take an unlighted incense stick. Okay, take an unlighted incense stick. Now, light the incense stick. Light the incense stick and keep it at the corner of your room. Okay, now I am going to keep this incense stick at the corner of this room. Right, I kept the incense stick at the corner. Okay. Now, I can find the difference. I can smell the incense stick even from the distance. What do you understand from this? So, from this activity, you can understand that particles are continuously moving in the air. That is why I can smell the incense sticks even though I am standing in from the distance. Okay, so particles are continuously moving in the air, right? Next we can move to the second activity. For the second activity, you need 2 beakers, glass beaker, right? And then blue ink or red ink. I am going to use blue ink, and then honey is needed. Okay, these things are required for the second activity. So now I am going to add some water into the first beaker. This is first beaker and this is the second beaker. I am going to add some water into it. Right. So in the second beaker also I am going to add some water. Right. Now, in the first beaker, add a drop of red ink or blue ink. Right? Drop of blue ink I am going to add now. Okay. So, in the second beaker, add a drop of honey into it. Right. Leave them undisturbed. You should not disturb the beaker. Right. Now closely observe the beaker. See the ink drop. Okay, you can find the difference after adding ink as well as honey. Right. See, the first beaker, the ink is evenly distributed as compared to honey, right? See, the ink is evenly getting distributed at less time when compared to honey, right? So, what do you understand from this activity? drop, okay, the ink drop moves faster as compared to honey. Why? Because the density of honey is more than that of ink. Okay. So the particles in the ink is evenly distributed, as well as the particles in the ink diffuses fastly. Diffuses means spread fastly as compared to the particles in honey. Okay. So based on the density, the particles are continuously moving, right? Okay. So you will get the assignment, children, today. So complete the assignment and send it through WhatsApp group, right? The next in the next video we will see the what you will get the revision video for unit test 1. Okay, get ready for that. Thank you, children.